In this video, we will look at how to graph a two-variable equation, and then we will look at some techniques that will enable us to graph the equation efficiently. Let's say we want to graph the equation equal x squared. This is a two-variable equation because it has two variables, x and y, where y is dependent on x. We can graph this equation by substituting different values of x and calculating the corresponding values of y. We substitute every value from the x column into the equation, solve for the corresponding y value, and plot the points on the graph. After plotting the points, we can connect the points to get the graph of the equation y equal x squared. However, this graph is not complete yet. We might have missed some points. Let's try substituting some negative values of x into the equation. Just like positive x values, we will now substitute the negative values in the equation, solve for the corresponding y value, and plot the points on the graph. After plotting the points, we can connect them to get the complete graph of the equation. A graph is complete when enough points are plotted such that it is obvious to the viewer what the shape of the graph will look like, and any rest of it will be just continuation of the same shape. So the obvious question is, how do we know when we have plotted enough points to make the graph complete? One way to obtain the complete graph is to plot enough points on the graph for a pattern to become evident. But that might require a lot of points for some equations and might be less efficient. Also, how do we even know if we have plotted enough points? Luckily, there are some techniques that can help us graph the equation efficiently and accurately for most equations. These techniques include making use of intercepts and symmetry. So let's look at these concepts first. Intercepts are points where the graph of an equation crosses the x-axis or the y-axis. The x-intercepts are points where the graph crosses the x-axis, and y-intercepts are points where the graph crosses the y-axis. In addition to visually identifying the intercepts, we can also solve for the x-intercepts by setting y to 0 in the equation and solving for x. Since each x term in the equation is multiplied by another term, we can set each term to 0 and solve for x. Solving for x, we get the x-intercepts as shown in the graph. Similarly, we can solve for the y-intercept by setting x to 0 in the equation and solving for y. Solving for y, we get the y-intercept as shown in the graph. Now, let's look at the concept of symmetry. Symmetry is a property of a graph where the graph is symmetric about a line. There are three types of symmetry that we will look at. Symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. Let's start with symmetry with respect to the x-axis. A graph is symmetric with respect to the x-axis if, for every point xy on the graph, the point x negative y is also on the graph. For example, the graph of the equation points 1, 1 and 1, negative 1 are symmetric with respect to the x-axis. Similarly, the points 4, 2 and 4, negative 2 are symmetric with respect to the x-axis. We can also determine if the graph is symmetric with respect to the x-axis by examining its equation. If the equation remains the same when y is replaced with negative y, then the graph is symmetric with respect to the x-axis. In this case, this is indeed true because square of negative y is equal to square of y. Now let's look at symmetry with respect to the y-axis. A graph is symmetric with respect to the y-axis if for every point xy on the graph, the point negative xy is also on the graph. For example, the graph of the equation points 1, 1 and negative 1, 1 are symmetric with respect to the y-axis. Similarly, the points 2, 4 and negative 2, 4 are symmetric with respect to the y-axis. We can also determine if the graph is symmetric with respect to the y-axis by examining its equation as well. If the equation remains the same when x is replaced with negative x, then the graph is symmetric with respect to the y-axis. Because square of negative x is equal to square of x, the equations are indeed the same. Finally, let's look at symmetry with respect to the origin. A graph is symmetric with respect to the origin if, for every point xy on the graph, the point negative x negative y is also on the graph. For example, the graph of the equation points 1, 1 and negative 1, negative 1 are symmetric with respect to the origin. Similarly, the points 2, 2 and negative 2, negative 2 are symmetric with respect to the origin. And as you might have guessed by now, we can determine if the graph is symmetric with respect to the origin by looking at its equation. If the equation remains the same when x and y are replaced with negative x and negative y respectively, then the graph is symmetric with respect to the origin, which is indeed the case for this equation. Now that we have looked at the concepts of intercepts and symmetry, let's look at some techniques that will help us graph the equation efficiently. For most equations, we can graph the equation efficiently by following these steps. Let's take an example equation y equals x cubed and follow these steps to graph the equation. As a first step, we will find the x-intercepts by setting y to 0 in the equation and solving for x. After solving, we find that the x-intercept is at x equals 0. We can now plot the x-intercept at the point 0, 0 on the graph. Next, we will find the y-intercepts by setting x to 0 in the equation and solving for y. After solving, we find that the y-intercept is at y equals 0. Since the x and y intercepts are the same, nothing new is added to the graph. Third step is to determine if the graph is symmetric with respect to the x-axis. To do this, we replace y with negative y in the equation and check if the equation remains the same. Since the equation is not the same, the graph is not symmetric with respect to the x-axis. Next, we will determine if the graph is symmetric with respect to the y-axis. To do this, we replace x with negative x in the equation and check if the equation remains the same. Clearly, the equation is not same again, so the graph is not symmetric with respect to the y-axis. Similarly, we will determine if the graph is symmetric with respect to the origin. To do this, we replace x and y with negative x and negative y respectively in the equation and check if the equation remains the same. This time the equation is the same, so the graph is symmetric with respect to the origin. Next, we will randomly solve for some positive x values for the equation and use symmetry to plot additional points on the graph. Let's take values of x as 1 and solve for y in the equation. Then we plot the point 1, 1 on the graph. Similarly, we can take values of x as 2, solve for y in the equation and plot the point 2, 8 on the graph. Now, since we know that the graph is symmetric with respect to the origin, we can plot the points -1, -1 and -2, -8 on the graph without the need to solve for y. Finally, we can sketch the graph using the points we have plotted so far. Notice that we didn't have to solve for y for all the x values to plot the graph. We were able to efficiently graph the equation by following the concepts of intercepts and symmetry. And that's it for this video. If you found this video helpful, please like and subscribe to our channel. In the next video, we will look at lines and their properties in detail. Thanks for watching.